All right, well, now that we can convolve functions, now that we have the convolution, it sort of makes you want to ask the question, what is the Laplace transform of a convolution? This seems like it's going to be really terrible, and I'll admit that the calculation is a little tricky, but stick with me. So just according to the definition of the Laplace transform, this is the integral from 0 to infinity of e to the minus st times the convolution of f and g evaluated at t dt. So this is the integral from 0 to infinity of e to the minus st. And what is this convolution? Well, that's the integral from 0 to t of f of tau times g of t minus tau, d tau. And then remember we have an integral dt. Okay, so this exponential here, since it doesn't have any taus in it, we're free to move it in or out of this integral with respect to tau. So let's move it inside that integral. So integral from 0 to infinity, integral from 0 to t, e to the minus st, f of tau, g of t minus tau, d tau, dt. Now this expression, if you haven't seen multiple integrals before, this expression might seem a little threatening, but don't be intimidated. It just means you do the tau integral first, and then you do the t integral when you're done with the tau integral. Unfortunately, we can't, looking just at the tau integral, there isn't really any obvious thing to do here. So it seems like one thing we might try is rearrange this to do the t integral first. But to do that, we have to think about, well, what region of tau and t values are these integral bounds talking about? Well, let's draw a picture of the tau t plane to see what region in the tau t plane we're working with. So t, let's put t on the horizontal axis and tau on the vertical axis. This is an arbitrary choice. You could put them the other way. You get a slightly different picture, but the result would be the same. Not the resulting region, but the result in the calculation. So our t values are going from 0 to infinity. So along the t-axis, we need to worry about all of these t values. And then for any single t value, in the tau direction, we're going from 0 up to, right, so maybe call this t naught. We're going from 0 up to the t value that we're at. So up to the tau value, t naught. Okay, and we're doing that for every single t value. So that would be like this. And if you look at all of the points in this region, well, it's all of these points. Everything in the first quadrant that's underneath the line t equals tau. Okay, well, you can see that we got this by taking this region in the t tau plane and slicing it vertically. But if we sliced it horizontally, we would get an integral that has the tau integral on the outside instead of the t integral on the outside. So let's see what happens when we slice this integral the other way. So we're going to put the tau integral on the outside and the t integral on the inside. Again, if you haven't seen multiple integrals before, this might seem a little strange, but it is a kind of a standard trick or a standard procedure of multiple integrals like this. So what tau values, so remember the integral on the outside, it doesn't know anything about t, it only knows about tau. So we have to think about what tau values are represented on this region. Well, every tau value from 0 to infinity is represented on this region. If you sort of take this blue region and squash it sideways onto the tau axis, it covers the entire positive tau axis. So in the tau direction, we need to go from 0 to infinity. Okay, and then what about for a single tau value? So what about for a single tau value, tau naught? What t values show up along this slice? Well, along this slice, the first t value that we get is the same as the tau value that we're at, because this point is on the line t equals tau. So the lowest t value is tau. And then the highest t value, well, this blue region extends infinitely far to the right, so the largest t value, t actually goes to infinity. Okay, so that's how we can adjust our bounds when we switch the order of integration here. This process doesn't affect the integrand, so the integrand is still e to the minus st f of tau g of t minus tau. But now we have our t integral on the inside instead of our tau integral on the inside. Of course, the question is, does that help? I mean, does it actually do us any good? But it does do us some good, because if you look right here, f of tau doesn't have any t's in it. So this part, f of tau, acts like a constant as far as the t integral is concerned. And that means we can move it outside of the t integral. So we can move it over here. So f of tau. Okay, times the integral from 0 to infinity, not 0, sorry, integral from tau to infinity of e to the minus st g of t minus tau dt d tau. Okay, now things are starting to look pretty good to have a Laplace transform show up, except it's not quite a Laplace transform because the bottom bound here isn't 0, right? The Laplace transform has a bottom bound of 0. So what we can do to fix this is introduce a new variable. Let's call it, I don't know, how about x? And x is just going to be t minus tau. Now, this inside integral is with respect to t, so when we do this substitution, we do have to compute the effect on differentials, but it turns out dx is just dt. So when we do the substitution, we get integral from 0 to infinity, f of tau, and remember, everything in this inner integral is inside of the d tau integral. Okay, then the inner integral is the integral, so we have to adjust our bounds here. When t, this tau right here, the bottom bound in the inside integral, that's a t value. So when t is tau, x is 0. So the bottom bound in our x integral is 0. And when t goes to infinity, x also goes to infinity. So the top bound is infinity. dt is dx. Okay, g of t minus tau, that's just g of x. And then e to the minus st, that's e to the minus s times, well, this equation that has t in it, we can rearrange it to find t. So t is x plus tau. So e to the minus s times t, which is x plus tau. Okay, it's a little hard to know if this looks like progress, but, you know, it's a little suspicious that we have a tau inside of this inner integral. We've seen that what we're trying to do is get the taus out of the inside integral. That's why we moved f of tau way over here. So we can do some algebra on the exponents to split this up. So we get integral from 0 to infinity of f of tau times the integral from 0 to infinity of e to the minus sx times e to the minus s tau g of x dx d tau. Okay, well that's definitely progress, because now this e to the minus s tau, it doesn't have any x's in it, and so we're free to move it outside of the x integral. So we get integral from 0 to infinity of f of tau times e to the minus s tau times the integral from 0 to infinity of e to the minus sx g of x dx d tau. Now, as sort of the final trick, look at this inside integral. It doesn't have any taus in it. So as far as the the tau integral is concerned, this inside value that is this big integral, it's a constant as far as the tau integral is concerned, and so we can move it outside of the tau integral. And the result is the integral from 0 to infinity of f of tau e to the minus s tau d tau times the integral from 0 to infinity of e to the minus s x g of x dx. But, we recognize both of these. This first one is the Laplace transform of f times, and the second one is the Laplace transform of g. So look at that. What we started with was the Laplace transform of f convolve g, and what we found was the Laplace transform of f times the Laplace transform of g. So that's really a big surprise, and I think this shows us two things. So first, this kind of explains why the false product rule for the Laplace transform, that the Laplace transform of f times g, it's sort of an easy guess to make that this should be the Laplace transform of f times the Laplace transform of g. Now we see why this can't possibly be true. It's because this product of Laplace transforms is actually the Laplace transform of f convolve g, not f times g. The other thing that this result tells us is that whatever convolution is computing, it's a little hard to get an intuitive grasp on what a convolution is, but this shows us that whatever convolution is computing, it's something that makes sense. It's something that's real, because when you take the Laplace transform of the convolution, you get something that makes sense, something that's manageable. And that's sort of the math gods telling us that the convolution is a sensible thing to do.